Okay, well, so thank you very much for inviting me to this conference. Thank you to Ali Genger and all the organizing committee for this wonderful conference. And in fact, I changed the title of my talk since after a year there were more analysis that I developed which allows a further understanding of this compound. So the title, I changed it to Incommensurate Magnetic Phases of the multiferroid compound manganese chromium oxide described with the superspace formalism. So first, I will give a little introduction about this compound under study and the theory behind this symmetry analysis. Then I will explain the previous experiments that were performed, and then I will talk about the global symmetry of each of the magnetic phases observed in this compound. Okay. So first, these chromium oxide spinels are systems in which there is an interplay between different physical properties, and several physical effects have been observed, which include the magnetization, multiferroicity, spin frustration, and more. And these compounds, as we can see here, they form a cubic structure in which the A sites are occupied by H2 plus ions, forming a diamond sublattice, and the B sublattice is occupied by chromium 3 plus ions, forming a pyrochlore sublattice. In these compounds, the main magnetic interaction is a strong antiferromagnetic exchange interaction between the chromiums, and then we expect a high degree of frustration in the tetrahedra forming this pyrochlore sublattice. When these systems have a non-magnetic A ions, this magnetic frustration is released by a spin-Janterer effect, in which the lattice distortions change the values of these competing interactions. But when you have magnetic ions in these A sites, this magnetic frustration is released by interactions between these A and B sites, and then there is no structural phase transitions. And also, this interplay between the A and B sites usually generates complex low-temperature magnetic ordering. And in particular, for this manganese chromium oxide, the ground state is controversial because the reported structures investigated by different groups are not consistent. Usually, these complex low-temperature magnetic structures are incommensurate structures, which mean that they are modulated structures without periodicity. So, to describe these structures, we use a basic periodic structure plus magnetic modulations with a propagation vector. So then we can express the magnetization as a Fourier sum of these magnetic modulations. In the case of only one propagation vector, this expression is further simplified, and we can observe that this superspace is 3 plus 1 dimensional, since this x4 coordinate corresponds to the product of the propagation vector and the position of the atom in the unit cell. Okay. Usually, to analyze the symmetry of these incommensurate structures, we use the representation analysis, in which if we consider H to be the Hamiltonian of the system, we know that it must be invariant under the symmetry group of the crystal that leaves also this propagation vector invariant. And to the set of matrices describing the transformation of these magnetic moments under the application of this symmetry group, we call it the representation of GK. And usually it's interesting to reduce this representation into its irreducible representations, since from the Landau phase of theory of phase transitions, we know that when a symmetry break takes place at this phase transition is due to the condensation of one or a set of collective degrees of freedom, which transform according to a single irreducible representation. And then the usual steps to determine the symmetry of these phases is to determine experimentally, by neutron experiments, for example, the propagation vector, and then with that we can determine this symmetry group and its irreducible representations, and we can build up a representation of this group and reduce it into the irreducible representations. And then for each of these irreducible representations, we can try to fit the data obtained from the intensity of the scattered neutrons to the models that, according with the symmetry, generates the intensity of the peaks observed. But another way of also analyzing the symmetry of these magnetic structures is to use a similar approach as in the Subnikov groups, in which, for example, for commensurate magnetic crystals, we use the symmetry operations are the ones that keep the energy invariant and the system undistinguishable after applying these symmetry operations. And these are rotations, translation, space inversion, or time reversal operations. And then these symmetry operations are determined by the magnetic space group. But in the case of the incommensurate modulated structures, we can add another kind of symmetry operations, which are the phase shifts in these modulations in the fourth dimension. That keep also the energy invariant. And then the symmetry operations in these structures are determined by the magnetic superspace group, which is more restrictive regarding the symmetry of the crystal than with the representation analysis. Okay. So from previous experiments in this compound, it was synthesized by a mixture of manganese oxide and chromium oxide under a reductive atmosphere of argon and hydrogen. And we perform a specific heat and magnetization measurements in a single crystal synthesized with the same method as for this powder. And we perform a specific heat at zero field and zero field magnetization measurements. And also we perform neutron powder diffraction experiments in this compound. With all this information from the experiments, we could construct the following phase diagram that I will show here, in which we can observe three different magnetic phase transitions. In the case of the nuclear structure, we didn't observe any nuclear phase transitions, but for the magnetic structure, we know that when the system is cooled below 40 Kelvin, there is a ferrimagnetic order which appears, in which as we can see, for example, in here in the neutron diffraction experiments, the peaks that increase the intensity are the same as the nuclear peaks, which correspond with a propagation vector 0, 0, 0. But as we cool down below 20 Kelvin, new peaks appear, which cannot be indexed by the nuclear structure, and can be indexed by a propagation vector delta delta 0, with the value of delta given here. And also for below 18 Kelvin, there is another satellite peaks that appear, which can be indexed by a different propagation vector. And I will show later what is this symmetry, the magnetic structure in each of these magnetic phases. So, in the case of the paramagnetic phase, this is the typical cubic structure of these magnetic spinels with this space group, in which all the atoms in the unit cell are generated by applying these symmetry operators to these special Wyckoff positions. Okay. But in the case of the ferromagnetic phase, if we use the representation analysis, we can build the representation of this space group for the propagation vector 0, 0, 0 for the different Wyckoff positions. And we know that we can observe that only there is this MgM4 plus is the only irreducible representation present at both sides. So we know that this is the representation that describes this phase transition to a ferrimagnetic order. However, this irreducible representation only imposes one constraint, that is that all the manganese atoms have the same magnetic moment and all the chromium atoms have the same magnetic moment. But it doesn't impose any constraint regarding the direction. So then we have still six parameters to describe this magnetic order. But if we use, well, here there are the software that you can use to obtain this symmetry analysis. If we use the analysis of the magnetic space groups, in which for this space group and the Wyckoff positions and using this irreducible representation, we know that there are 6 possible magnetic subgroups compatible with this information. But only one is compatible with the magnetization experiments, where we know that the net magnetization is pointing around the 1 minus 1, 0 direction. And then we know that we can describe this ferrimagnetic phase. So we can see here the manganese and the chromium spins interact antiferromagnetically. And we see that the chromium and oxygen atoms are split in the unit cell, and we'll see that there are a loss of symmetry. This is okay. For this delta zero phase, we perform the same analysis for the representation of this system. We see that in this case all the irreducible representations are present in both positions. And then this analysis doesn't tell us what can be the symmetry of this low temperature phase. However, if we do in this case, use the superspace group formalism for this incommensurate structure, we know that for the MGM4 plus irreducible representation, which corresponds with this propagation vector 0, 0, 0, and together with another irreducible representation, which can be one of these four ones, for this other propagation vector, we obtained several possible magnetic subgroups. And then we did a systematic trial and error of fitting the data to see which can be a good model. And in this case, we obtained a good fit for using an irreducible representation, which is MSM2, which corresponds with this superspace magnetic group. And in this case, we can see here that it develops a conical order in which this delta zero vector, propagation vector, is in the 1, 1, 0 direction, and the magnetic atoms are still coupled antiferromagnetically, but in this case there is a conical order, transverse conical order. Similarly, for the lowest temperature magnetic phase, we perform the same analysis. In this case, there is only one irreducible representation, but this doesn't impose any constraint in the magnetic symmetry. And in the case that we use the incommensurate approach for the superspace group formalism, we obtained only two magnetic subgroups, and only a good fit was possible for this superspace group, in which there is a complete loss of symmetry. And in this case, the propagation vector is in a random direction. And as we can see here, the order is more complex, and it's difficult to visualize this propagation vector. And also, it was a good fit we obtained a good fit for these conical structures, but in this case, they are not perpendicular to the propagation vector. And with all this analysis that we perform with the superspace group, we can define this net magnetization and these components. And we know that in these compounds, there can be electric polarization, which is given by the spin current model, in which this polarization is proportional to the vectorial product of the propagation vector and the net magnetization. And thus, we know that for transverse conical modulations, there can be an electric polarization. And this compound can be a multiferroic. We can also predict the direction in which this electric polarization is developed. In the case of this delta zero phase, we observed that in previous studies, in this case, for example, they prepare a powder sample. They observe this polarization below 20 Kelvin. And also, in another different study, they also observed this signal, this electric polarization, below the phase transition. In this case, they observed this in the 111 direction. Okay. However, for this delta 1, delta 2, delta 3 phase, which is the lowest temperature phase, there is, if you go see these previous studies that were performed, you don't see that they haven't observed this phase in any other compounds. Here, for example, there are experiments, studies in which they did neutron diffraction, but they only observed this delta zero phase, not this lowest temperature phase. However, this can be explained because in our case, I didn't show it here, but we also prepared this sample with different methods, for example, under an air atmosphere, And when the sample is synthesized in a different condition, we observe also that this lowest temperature phase is not developed. And then the explanation could be that in these previous studies they haven't considered this synthesis method, and then they cannot observe. But it would be interesting to perform polarization measurements at this lowest temperature phase to observe if this is also a multiferroic. Okay, so then we have here reinvestigated this compound by different microscopic characterization and neutron diffraction experiments. We see that there is a new magnetic phase, which depends on the synthesis method identified under 18 Kelvin. And we know that using the superspace group formalism, we can predict the existence of multiferroicity at low temperature phases, and also derive the electric polarization vector for each of these magnetic phases. And that was all. Thank you very much for your attention.
Thank you very much for this very interesting talk and for staying on time.
Yeah, I was wondering if from neutron scattering experiments that you have performed, you can deduce the interactions, the interaction parameters that are responsible for this magnetic order. I mean, the exchange constants and the vector.
Well, from the neutron diffraction, I don't think. Considering also these macroscopic measurements of the magnetization, you can construct a model in which you know that the competition between the manganese and chromium is stronger than the interaction between the chromiums and between the manganese. But there is still no clear, let's say, model of how exactly these interactions are interacting between each other.
So maybe they can be inferred from other kind of measurement.
Yeah, but we haven't performed the.
But which kind? I'm interested in which kind of measurements would give you this information. If you know, I mean, otherwise, I mean, we can discuss it later. I don't want to push too hard.
Yeah, right now.
Okay. Then no. I was just interested in neutron scattering, which was what you presented. Within elastic.
That's the same that we did in the carbon flight.
Any other question? Can I ask you a quick question? I think, well, you mentioned that you see three magnetic transitions, and you mentioned that there is no structural transitions associated to it, but when you see that there is a multiferroid, I mean, there is a coupling with the polarization with the ferroic properties, how can you interpret a lack of structural transitions and a change to the ferroic properties?
Well, in this case, in these models, there are lattice distortions.
Okay.
For example, in the position of the oxygen, which allows to release this magnetic frustration, and then this distortion in the oxygen position allows also to this polarization. But there are there is no symmetry change in the structural.
I see. Okay, I understand. Thank you very much. Okay, if there is any other question, if not, we can close the session. Thanking all the speakers again for the presentations. And before we finish, let me just give you this certificate for your presence. Thank you very much.
Thank you.